The following content is supported by victoris.org.
Now in question 3, we're given a projectile that is fired off at an angle theta and the initial velocity u. We need to show that the range of this projectile is given by the following expression. This is just a kinematics question, and the first step will be to find the amount of time that the projectile spends in the air. To do so, we consider the vertical component of velocity, and we want to solve the value of t such that the vertical velocity has flipped from u sine theta to minus u sine theta. This is the velocity way, but one can also use the displacement way, which will require the quadratic equation. Both ways are correct, and eventually we'll obtain the time of flight to be this. Now that we know how long the projectile stays in the air, we can just find the range by substituting in time, and that gives us the following expression. Notice that u squared and g are constants, and the only thing that varies is theta. In order to find the maximum range, we just need to find the value of theta that maximizes r. Since the value of sine theta can be maximized by setting theta equals to 45 degrees, the answer for the maximum range of the projectile is just u squared over g. Substituting values, we get the following expression. Now we're given a variant of the question where the projectile is set off a slope instead. Now in part 1, we're asked for the expression for the time of flight in terms of the constants given in the diagram. Your initial idea might be to find the time of flight using the vertical component like we did for the previous part. But in this case, there's actually an easier way because we're given r as a known value. So it's simply the horizontal distance divided by the horizontal velocity. Now part 2 is just trigonometry. And part 3 asks us to combine our first two parts to get an equation for the range. Now this is where kinematics equations come in. For the vertical component, we can use the standard Szilard equations. Vertically, the Szilard equations take the form as such. And what's nice about this is that now we have t from part 1 and we have sy from part 2. Substituting in the following expressions would give us this, and just simplifying it down would give us the answer that we want. Now we want to show that part AI is a special case of the general equation that we obtained in part B, part 3. And this is always a good sanity check to do whenever you have obtained a more general expression. In this case, the special case is when the slope has an angle phi of 0 degrees. So it just amounts to substituting phi equals to 0 into the following expression, and that gives us the original equation. Now for the last part, we're asked to find the given value of theta. That just amounts to finding the value of theta that maximizes the range r given in this expression over here. How do we maximize a function with respect to a variable? We take a derivative and set it to equal to 0. By right, we also need to check the second derivative to make sure that it is a maximum and not a minimum, but in most physics questions, this is not required. Just performing the derivatives gives us the following expression, and we need to massage the trigonometry a bit to get the expression of theta in terms of phi. Now once again, we can perform another sanity check to make sure that when we substitute phi equals to 0, we just get theta equals to pi over 4, which agrees with the previous answer for 45 degrees.